Welcome back. In this lesson, we'll see how to read digital inputs and debounce switches connected to them. Keep in mind that you can refer back to the PDF version of this tutorial, which you can download for free from the Gum Electronics website, to fill in any details this video skims over. In the last lesson, we were still blinking LEDs. Now that's more useful than it sounds because, with appropriate drive circuitry, you can replace that LED with any on-off device you want to control. But unless your device will just run a fixed output sequence, it's going to need to respond to inputs from the outside world. And the simplest type of input, which we'll look at in this lesson, are digital inputs, on or off, high or low. We use a simple push button switch, but it could be anything that indicates an on-off status. We'll use the same circuit as before, with an LED driven by GP1, but now with a push button switch connected to GP3. The 1K resistor isn't really needed in this example, but series resistors like this help protect the PIC's inputs from high or negative voltages, or from short circuits if the pin is accidentally configured as an output. When the button is pressed, GP3 is pulled down to ground through the switch. Otherwise, it's pulled up to 5 volts through the 10K resistor, which is why resistors like this are called pull-up resistors. So, GP3 will be high when the switch is open, and low when the button is pressed. To build this circuit with the PIC training board, leave it set up as before, but also close jumper JP3, which brings the 10K pull-up resistor into the circuit. So now we've got a switch connected to a pin. How can we tell if it's open or closed? As we saw back in lesson 1, each GPIO pin can be configured as a digital input or output, except for GP3, which is input only. To configure a pin as an input, set the corresponding twist bit to 1. The state of each pin can then be read in the GPIO register. If the voltage on a pin is high, the corresponding bit reads as 1. If the input's low, it reads as 0. So if the push button is pressed, the GP3 bit will read as 0. Otherwise, it would read as 1. But how can your program tell if a bit is a 1 or 0? There are a couple of PIC instructions for doing just that: BTFSS and BTFSC. BTFFS skips the next instruction if a specified bit is set to 1. BTFSC works the same way, but it tests for the bit being 0 or clear. Let's start with a really simple example to show how those bit test instructions work. We'll just light the LED whenever the button is pressed. Now you could do the same thing with a piece of wire, but hey, why not throw a microcontroller at the problem? As usual, I'll base this example on the initialization code and structure we've used before. Makes sense, right? By configuring the PIC for internal reset, the GP3 pin's external reset functionality is disabled, leaving the GP3 pin available for use as a digital input. I'll clear twist bit 1 to make GP1 an output, and leave bit 3 set to explicitly configure GP3 as an input, even though GP3 is input only. We'll start with the LED off, which means that the GP1 bit should be cleared, and in this case, we can do that by simply clearing the whole of GPIO. We need to set the GP1 bit to turn on the LED whenever the push button is pressed, and clear GP1 whenever the button is released. So in a higher level language, we might write something like this. Of course, we need to translate that pseudocode into assembly language. We can start by noting that whenever the button is pressed, the GP3 bit will be 0. And if the button isn't pressed, GP3 will be a 1, or high. So we need to test for the GP3 bit being set or not. And of course, that's where the bit test instructions come in. You just have to remember, they kind of work backwards. They skip the next instruction if the test is true. So to test for the button being down, I'm actually going to use BTFSS. So the instruction to turn the LED on won't be skipped when GP3 is clear. Seems backwards, doesn't it? Now we have to set the GP1 bit. And of course, there's an instruction that does just that. BSF sets a single bit in a file register. Similarly, BCF clears a single bit. So I'll use the BSF instruction to set GP1, which is bit 1 of the GPIO register, like this. Now I do much the same thing to turn the LED off when the button is released. Using BTFSC because we're acting on the button being up, and BCF because we're turning the LED off this time. Okay, that should work. Most of the time. Remember the read modify write problem from lesson 2? Instead of toggling the output pins directly like this, it's safer to use a shadow register. So I'll define a variable to use as a shadow copy of GPIO. Then it's possible to simplify the code a bit by assuming the button is up, setting bit 1 in the shadow copy only if the button is pressed, then copying the result to GPIO. Now if I assemble this code and program it into the PIC, the LED lights whenever I press the push button. It's not very exciting though, is it? It'd be better to turn the LED on when I press the button and turn it off again when the button's pressed again. There's a problem with doing that though. Real mechanical switches have contacts that bounce. Too fast for human perception to be sure, but fast enough for the PIC to see the switch go on and off a few times, really quickly, whenever the button is pressed. Let's see that in action. I've hooked an oscilloscope up to a push button, so I can see what happens when the button's pressed. The output's normally high, and it'll be pulled down to ground when I press the button. The scope's been set up to trigger on that, so we can capture the button press. So I'll press the button, and bang, there it goes. But it's hardly a clean transition. I'll zoom in a bit for a better look. There are definitely a couple of good bounces in there. I'll turn on some cursors so I can measure them. We can see that in this case, for this switch, the bouncing finishes after 133 microseconds. The first bounce starts 72 microseconds in, and the shortest bounce is just 9 microseconds long, which seems pretty short, but it's still plenty long enough for the PIC to react to. So we need a way to avoid reacting to those short pulses. You can use hardware approaches to filter them out, and a simple hardware method is shown in the written tutorial. But you can also do it all in software, and that's what we'll look at here. Let's start with some code without any debouncing. First, we wait for the button press. As long as the GP3 bit is set, the goto is executed, and the PIC sits in this busy wait loop. When the button is pressed, GP3 is clear, so the goto is skipped, and move on to toggling the LED, using XOR as we've done before. Then we need to wait for the button to be released, ready for it to be pressed again. You'll find that with this code, it's hard to make the LED change reliably, because each contact bounce looks like a new button press. So we need to debounce it. The easiest way to do that is to add a delay. The idea is simple. Respond to the button press immediately, so the device feels nice and responsive to the user, then wait a while, until we're sure that the button will have finished bouncing, before checking to see whether it's been released. Then we add another debounce delay, to be sure the button's stable after the release, before going back and waiting for the next button press. How long to delay? It depends on your switch and your application. The switch I tested before always finished bouncing within a couple of hundred microseconds, so a delay of a millisecond should be safe, but it doesn't hurt to make it longer, as long as the button still feels responsive to the user. Luckily, we have a handy 10 millisecond delay module that we prepared earlier, so I might as well use that. I'll start by adding the code to make the external delay module accessible. Then call it to generate a 10 millisecond delay after toggling the LED after the button press. And then again after the button's released. You'll now find that you can reliably toggle the LED on each button press. There's still a potential problem though. Sometimes you get short spikes or glitches in input signals, maybe from some sort of electrical interference, but if you only have a simple debounce delay, there's no way to tell the difference between a glitch and the start of a switch closure. A common way to filter out spikes, as well as bounces, is to check that the switch stays consistently open or closed. When you detect that the button's pressed, you keep checking, until it's stayed down for long enough that you're confident that it's really pressed and it's stopped bouncing. You can do that by periodically sampling the input and counting the number of times it's still in the new state. In other words, if a switch reads on enough times in a row, it's really on. This debounce routine is one way to implement that counting algorithm. The inner loop is 768 microseconds, because we only need 3 instructions to make a delay that long, and it's unlikely that any individual spike or bounce will last longer than that. Then, if we say that the button has to stay down for 10 milliseconds before we accept that it was pressed, we'll execute the inner loop 13 times for a total of around 10 milliseconds. Each time around the outer loop, we check the push button, and if it's up, restart the process, because we're looking for it to be down 13 times in a row. But if it's down, we keep decrementing the counter until it reaches 0. And yes, that's decrement, not increment, because it's easier to write it this way than starting from 0 and counting up. So it's not exactly the same as the pseudocode version, but it has the same effect. Now we have our debounced button press, so we can safely go ahead and toggle the LED. Finally, wait for the button to be released, before going back and waiting for another button press. We'll use the same counting algorithm to ensure that the button's really been released and stopped bouncing. The only difference is we'll use the opposite bit test instruction, restarting the count if the button's down, because we're waiting for it to go up. Okay, we now have a robust, reliable bit of code for toggling an LED each time a push button's pressed. The code's fine, but there's still an improvement we can make to the circuit. This arrangement of using a resistor to pull up an input when a switch is open is so common that most microcontrollers, including PICs, make them available internally. If you enable the internal pull-up, you don't need the external pull-up resistor, so it can go, and we're left with an even simpler circuit. To take the external pull-up resistor out of circuit on the training board, just remove jumper JP3. The internal pull-ups are controlled by the GPPU bit in the option register. The option register controls a few other things, which we'll take a look at in future lessons. But to enable the pull-ups, we only need to clear the GPPU bit. So I'll add some instructions to do that to the initialization code. Option is a little like tris, in that it's not directly accessible. Instead, you load the value that you want to load into it into W. Then you use the option instruction, like this. By the way, this style of commenting is supposed to show that we only care about what the GPPU bit is set to. The other bits don't matter in this program. When you assemble this code, you find it now works fine with no external pull-up resistor. And that's it for the PIC assembly language video tutorials. There are some more assembly language instructions to learn, of course, and they're covered in the written tutorials. But the instructions we've seen so far are the most common, and they'll give you a good platform to build on. We've covered most of the baseline PIC core, so from this point on, it's mostly about learning how to use the PIC's peripherals, such as timers and analog to digital converters, and I'll be covering those in the PIC-C video series. The principles are exactly the same. C just makes it much easier to focus on the peripherals themselves, instead of on the instructions for accessing them. Sorry for the pun, but see you!